Well, welcome to the video lecture for topic 3 in channel hydraulics, and this will be in two parts. In this first part we'll deal with the derivation of the gradually varied flow equations, and we'll deal with two topics. Firstly, we'll talk about when the situation when flow resistance and downstream hydraulic controls are important in determining water levels, and then we'll go on to derive the three gradually varied flow equations. So we've talked previously about situations where depth can be controlled by flow resistance under uniform flow conditions where the gravitational force exactly balances the flow resistance force. We've also talked about this situation where the water depth is controlled by a downstream hydraulic control under subcritical flow conditions, such as upstream of a weir. In fact, the normal situation in most open channels, predominantly along the length of the open channel, is for both flow resistance and a downstream control to determine the water levels and flow velocities. So the downstream end of this backwater profile, so we've got a backwater profile, it's a classic M1 profile, subcritical flow with a hydraulic control at this downstream end. And so the downstream end, water levels are almost entirely controlled by the height of the water over the hydraulic control, this weir. And at the upstream end, we have normal depth and uniform flow. And at this situation, water depth is entirely controlled by flow resistance. However, along most of the channel, it's the situation is gradually varied flow, and the water surface profile and water depths are controlled both by the level at the downstream control and by the flow resistance along the stream channel. So let's think about this firstly mathematically. How do we model this situation of gradually varied flow? How do we model the water surface profile? Well, let's add in the energy terms. We're going to use conservation of energy to do this. We have the depth term and the velocity term. The three gradients: the bed gradient, the water surface gradient, and the total energy gradient. And we know that the change in total energy head is given by the change in the sum of these three terms, and that's expressed as the gradient in the total energy head, SF. So this is just simply saying the gradient in the sum of the three energy terms is equal to the gradient in the total energy head. And we can move the Z outside of the differential, dz dx, and we know that dz dx is equal to the bed gradient, and so we can rewrite this as to be the gradient in the specific energy equals the bed gradient minus the energy gradient. If we take that expression and we know the formula for the specific energy in an open channel, and we differentiate that with respect to depth, we get this term, this expression. Using the chain rule, dd dx, the depth differentiated by the distance along the channel, equals the depth differentiated by the specific energy times the specific energy differentiated by the distance along the channel. And so we can get dd dx equals dd dE, which is the inverse of this expression up here, which is the EDE, times dE dx, which we know from up here is S0 minus SF. So we get dd, the change in depth with distance along the channel, equals the bed gradient minus the energy gradient divided by this term. And this term here is the Froude number squared. So it's S0 minus SF over 1 minus Froude number squared. So we actually have three equations then for gradually varied flow. The first one is that the change in the total head is equal to the energy gradient, or the negative of the energy gradient. the change in the rate of change in specific energy along the channel is equal to the bed gradient minus the energy gradient, and the change in water depth along the channel differentiated by distance along the channel is equal to S0 minus SF divided by 1 minus Froude number squared. Excuse me. Okay, so you can work through that more slowly yourself to reassure yourself that those three equations are valid. One relates to total head, one relates to the specific energy, and one relates to the water depth. They're all essentially saying the same thing. It's an expression of the conservation of energy along the channel. Now these three equations, we apply these to model water surface profiles. And to this we solve these equations numerically, and there's two general approaches for doing this. There's the direct step method and the standard step method. In the direct step method, we consider for a given change in depth, in water depth or in stage, what's the distance upstream we go to get that depth. So we set the change in depth and we calculate the distance upstream. In the standard step method, we work out the change in depth for a fixed distance, a fixed step. So direct step, we have a fixed change in water depth or stage. For the standard step method, we have a fixed distance upstream and we calculate the change in depth. We have the three alternate equations for gradually varied flow. We use the last of those, which gives us which is the equation for the change in depth with distance upstream. We use that with the direct step method, where we calculate distance upstream for a given change in water depth. We use the second one based on specific energy for the standard step method, where we have a regular channel. That's a channel which has a uniform channel shape. The channel shape doesn't vary along the channel. We use the first one using the standard step method, where we calculate change in depth for a fixed distance upstream, where we have an irregular or natural channel. It's this equation that's embedded in HEC-RAS, the sort of standard tool that's used for modeling water surface profiles in natural channels. So I'm going to go through those three methods: the direct step method for regular channels, the standard step method for regular channels, and then the standard step method for irregular channels. And that's the end of the first part of the video. In the second part, we'll work through the numerical solutions to these gradually varied flow equations.